Stanford University.
So it's my pleasure tonight to introduce my colleague Patrick Hayden, who's going to be telling us about the quantum computational universe. Patrick joined us at Stanford in 2013, and since then, he's been spearheading a world-leading research effort in quantum information and its overlap with studies of quantum gravity. His primary training was in the nature of quantum information, of how the quantum encoding of information differs from its classical encoding, enabling really striking applications, for instance, to quantum computation. But since coming to Stanford, and in fact before coming here, he's boldly ventured into studies of how ideas from the world of quantum information can also impact some of the deepest puzzles of quantum gravity. Puzzles such as the fate of information in the Hawking evaporation of a quantum black hole. Patrick's brilliance has been recognized with numerous awards, starting with the Rhodes Scholarship when he finished at McGill, then a Sherman Fairchild Prize Scholarship from Caltech when he finished at Oxford, and more recently a Sloan Fellowship and a Simons Investigator Award. So let's listen to what he has to say about the quantum computational universe.
Well, thanks a lot, Shamit, for the... Thanks, Shamit, for that very kind introduction. So the conceit of these lectures is that there's something that we can learn about the physical world by thinking about the nature of information, and particularly quantum mechanical information. And in my abstract, I mentioned this cliche, right? That is, these days it becomes hard to tell exactly where the boundary between the virtual world of information ends and the physical world of reality begins, particularly with the election that's about to happen tomorrow, when we're faced with a tsunami of misinformation and propaganda, which is kind of arises out of people tapping their fingers without regard to reality, and nonetheless influencing the minds of millions of people, and potentially tomorrow having a catastrophic or not so catastrophic positive effect on what happens over the next 4 years. These lectures are hopefully going to be devoted to a less negative way in which reality and information intersect. And that is really, I'm going to try to introduce to you the ideas of quantum information, quantum computation, and ultimately tell you something about how they are relevant not just to sort of engineering interesting devices, but to the structure of space and time and reality itself. So just to, most of you are probably aware of this, but just to get warmed up here, over the last, 25, 30 years even, there's been growing interest in how these strange features of quantum mechanics can be harnessed for information processing purposes, whether that's for communication or for computation. And there have been some striking successes in that regard. We've learned that if we could, we've actually built devices in which essentially cryptographic systems in which cracking the code amounts to a violation of the laws of physics. Actually, we haven't succeeded in building those, but we know how to build them in principle. We know that if we could build computers in which the internal state of the computer was intrinsically quantum mechanical, that it could do quite remarkable things, like factor large integers in a reasonable amount of time, which is something it is thought, at the moment, no classical regular computer can do, and it's thought that it will never be able to do. And so those are some of the successes. The effort of quantum information computation has also studied the limitations of what we can do information processing-wise with computation, partly with a regard to saying that if we can understand the limitations, then we'll find ways to get around them. And so again, in these lectures, what I'm going to do today, we're going to discuss the role of information in quantum mechanics. We're just going to get ourselves started. And I'll actually try to tell you a little bit about quantum algorithms, what we could do with quantum computers, and give you a sense for how they would operate, culminating in some understanding, although we don't have time to do all the details, of how Shor's factoring algorithm actually works. And then in next week's lecture, we'll talk more about entanglement, error correction, and the relationship between information and, let's say, holographic quantum gravity. We'll talk about decoding the hologram and how that's related to quantum information theory. So without further ado, let's get ourselves started here. And let's just discuss quantum mechanics and information in general terms. So I think a significant fraction of the audience tonight are regulars from Lenny Susskind's many courses on theoretical physics. I recognize some Stanford graduate students, even some Stanford professors. So many of you are familiar with quantum mechanics already, although I'm hopefully not going to assume too much of you. But we can have a conversation. So if I assert to you that information behaves strangely in quantum mechanics, and I asked you for examples, in fact, I'm asking you for examples, what would you say? Just stick up your hand and give me an example, a way that information appears in a somewhat surprising way in quantum mechanics. And not these fancy applications, just the basic theory.
Instantaneously?
So I mean more in sort of in the theory itself, as opposed to sort of physically. And it's not instantaneous, luckily. That would lead to great problems. Yeah.
The measurement itself, which generates information, is a very strange thing in quantum mechanics.
Yeah, okay, so let's just start there. Measurement is probabilistic. So this is a really weird feature of the theory of quantum mechanics. No other physical theory is like this. That there are equations of motion that tell you when you start off in a given state, how it's going to behave as a function of time. And then there's this extra rule that tells you how you actually convert the wave function, the quantity you calculate in quantum mechanics, into probabilities that you'll measure in the laboratory when you do an experiment. No other theory needs this extra rule that tells you how to interpret or how to convert what the theory predicts into measurement outcomes. And as far as we know, these probabilities generated by quantum mechanics are real. They're not a result of just ignorance, which is what most of the probability we experience in our lives is. According to Nate Silver, the probability of one side winning the election tomorrow is about 65%. That probability is a representation of our ignorance. It's not fundamental. Someone's actually going to win. There's an answer to that question. So that is a strange feature of quantum mechanics with respect to information, for sure. It seems that information is being created in some sense, or at least the way that it existed before the measurement was qualitatively different. Other ways? Yeah? Sorry?
Superposition.
Superposition, excellent. So superposition. So mutually incompatible states can coexist. That's just plain weird, right? That a particle can be here or there at the same time. A current in a wire can be flowing clockwise and counterclockwise at the same time, and so on and so forth. And again, for those of you who haven't taken Lenny's class, it's good to have an example in mind. And so we can think of a photon. Propagating here, and it hits a half-silvered mirror. And what happens when it hits the half-silvered mirror? Well, has a probability of half of going through, and a probability of half of not going through, getting reflected. Now, that wouldn't be so strange. In quantum mechanics, we represent the state as being a superposition of having gone through and having been reflected. We could do that with probabilities, right? That would be no problem. We could say, well, there's a probability of 50% that it went through and a probability of 50% that it got reflected. However, they're not just probabilities. Because if we insert a full silvered mirror over here and a full silvered mirror over there, the light will get reflected, and then another half silvered mirror. If we set the lengths of these paths properly, all the light will come out on one side. So this is my little measurement apparatus here, little, let's say a photodetector. So it's always here. And if we put detector there. We find it's never here. And so somehow, if they were just probabilities, if the photon went went through with probability 50%, it would come up, hit the second mirror, and with 50% of the time it would go up, and 50% of the time it would get reflected. And we'd see 50-50% in our, when we did our measurement. But that's not what happens. And so the photon, even though there's only one of them, somehow interferes with itself. The two branches of the wave function representing the photon traveling upwards or downwards through these paths. So superposition, the possibility of mutually incompatible states coexisting, I'd say, is kind of strange. What else? Yeah? Entanglement. Good. So entanglement is the special kind of correlation that exists between the states of, say, different particles of a quantum system. And actually today I'm going to have almost nothing to say about that, because it's a topic all its own. But next Monday we'll have more to say about entanglement. But it is definitely interesting and important. All right, so there are others. I guess this, maybe I'll throw these on just because I don't expect everybody to guess exactly what, to divine what I'm thinking. But measurement causes disturbance. And this is, of course, intertwined with the first observation, right? That the way it causes a disturbance is that the state actually jumps probabilistically to one of the possible outcomes of the measurement. And of course, I could mention the Heisenberg uncertainty principle, but everyone in the room is probably familiar with it. But the important thing about the Heisenberg uncertainty principle is it's not just a practical constraint on simultaneously measuring position momentum. It's a constraint on what it's possible to know about a physical system. It doesn't even make sense to ask what is the simultaneous position momentum of a physical system in quantum mechanics. That's just not something you can write down. And so there are epistemological, fundamental restrictions on what we can know that come from the structure of the theory. So with these simple observations that we've already made, I've said quantum information, part of it is about identifying the constraints on how we can manipulate information in quantum mechanics. And so let's see if we can derive one of those basic constraints just from what we have on the board here. And that's something called the no-cloning theorem. So with classical information, which we think of as bits usually, or we break it down to bits, something we do with it all the time is we copy it, right? We have Xerox machines, we have ever-proliferating email chains, we have, share on Facebook, et cetera, et cetera. We copy all the time. We don't even have to think about it. It works. It's easy. It's obvious. Now, suppose that, here's going to be my little picture. I have an electron, and the electron has a spin, right? It's spinning in some, has a part of its state is an orientation along which it's spinning, or an axis. And suppose we have this electron, but we don't know which direction it's spinning in, right? So someone just hands you an electron. It's spinning in some direction. You don't know which way. And the question is, can you build a device? So you let the electron enter into your fancy box. And your fancy box might be a laboratory the size of this room. It might be something small. I don't know. I don't care. Just something that's consistent with the laws of physics. And out of there should come two electrons. In the same orientation as the original. So I'll say same spin as the original. Or even state. No spin, good enough. And the question is, can you do this? Can you copy in quantum mechanics? Well, it's not a question. I've actually told you the answer. Now, I'll ask you, though. Can you argue to me, just based on what we already know about quantum mechanics qualitatively, without any equations or anything else, that no cloning is impossible? if we could do it? Would it lead to a problem with anything we've written on the board so far?
Well, just measurement.
Yeah, exactly, right. So if we could make a copy that was perfect, then we could take the second copy, say, and measure that one however we like. And then we could repeat, right? We could take the one, the electron that we didn't damage, run it through a cloning machine, and then measure it some other way. And so we could just keep measuring this original electron over and over and over again as much as we like, without disturbing the original. And so this contradicts. So this violates, what do we call it? Number 4. So just by virtue of the fact that we know that we can't measure without disturbing, that also means we can't copy. And these are just really just different ways of expressing the same fact. And it's sort of a very basic feature of quantum mechanical information that if you have good quantum mechanical information, it's inherently private, right? Because you can't copy it, you can't measure it without disturbing it, and so quantum information, if you want it to be good quantum information, you have to make sure that you don't copy it, or don't try to copy it, don't try to measure it, because all these things are going to cause disturbance. All right, so the goal for today, that was just an illustration. I suppose it's just an illustration of the kind of reasoning that we like to do in quantum mechanics, or in quantum information theory, where we try to think about the different processes, operational tasks that we might apply to quantum mechanical systems, and see how they're related. What's possible, what's not possible. And I took this, the easy way out when I was writing these observations on the board, where I was saying, oh, this is weird, this is strange. But the goal of quantum information is often is really to get away from that, right? To stop sort of just sitting there in useless awe or bewilderment, and instead actually try to operationalize your questions and develop some intuition and some understanding of what's going on in the theory by thinking about what you can practically, if only in a thought experiment, achieve or not achieve. So let's talk a little bit then. So what we're going to do for the rest of the day is we're going to think about quantum computation. Or I guess I have space here. So let's talk about computation. And we're in the heart of Silicon Valley, where many of the great inventions of the computer age were developed. And so we can talk about some of them, say this device may or may not, or a PDP whatever number. And that device may ring bells for some of you in the audience. Some of you may have programmed it back in the day. Oh, excellent. Something more current, we could talk maybe about an iPhone. We could even talk about a Google data center. So these, on the face of it, are all very, very different machines, right? The PDP-8 couldn't accomplish a lot. The Google data center, yeah. Yeah, it's been a. Is this hard to read at the back, by the way?
I think it might be good to use a black pen.
A black pen? Sure. Yeah. So put up your hand if you can't read at the back. Okay, I'll try to be bigger then. All right. So we have different devices here, and it doesn't even really merit discussion almost these days that they are essentially equivalent. Yeah, from the point of view of input being processed to output, modulo the fact that one is faster, that this one is faster than that one, and it has more memory, right? But if we souped up the PDP-8 with more memory and we're just willing to wait a little while, they'd be equivalent to each other, right? And that's because we can program one to simulate the other. It's not a very deep observation. But one can formalize this, right? So we build all these different kinds of computing devices, and the ones that we build these days, it's pretty obvious that they're all equivalent to each other. But you can scratch your head and try to be more inventive about how you'd build a computing device, right? And back in the day, people did. They were very inventive about how they built computing devices. So we can make a list. I'll draw right bigger here. way back in the day. I don't think there's anyone here who programmed these, is there? Yeah, okay, so yeah, we could have an abacus back in the 19th century. Charles Babbage invented these machines that actually performed computations mechanically as opposed to electronically. And of course, we have the computers we're familiar with. There was also a period of flourishing of a kind of technology that's pretty much dead these days, but analog computers, right? That if you wanted to solve some differential equations, and they were complicated, what did you do? Well, you had some mechanical, again, or electronic system that would evolve as a function of time according to some differential equations that you could write down, and you tuned your knobs, right? And that's how you simulated, that's how you solved your differential equations. And more, right? And so that gives rise to a hypothesis, right? Well, so it turned out, why don't we actually use these anymore? The reason we don't use them is because we don't need to, right? To the extent that they're useful for reliably giving us answers to things we want to calculate, we can simulate them on a digital machine. And maybe that's not quite as obvious, right? But it's true. And given all of the success of this effort to build computing machines, it's a reasonable hypothesis to just say, well, the basic architecture of machine that we work with today is all we need to talk about. That any physically realizable computation could be efficiently simulated, say, on a PDP-8 with enough memory. It might take time, but it could be done. So let's give this a name. We'll call it the strong Church-Turing thesis. I did this in the wrong order then. So, all physically realizable. Computations can be efficiently simulated. Let's say an iPhone. With external storage. And this isn't a theorem. This isn't a proven fact. It's sort of an empirical observation that anything anyone has succeeded in computing so far has pretty much satisfied this rule. And again, are there computer scientists in the audience? Okay, so a significant number, yeah. So whether you're practicing or theorists, theoretical computer scientists like to think of models of computation. And there's the model of computation that we're all familiar with, right? Or, well, idealizations of that. Let's say our iPhone with external storage. And they're mild generalizations. Maybe you supplement that with the ability to flip some random numbers. Doesn't seem to have a huge, huge effect. They also think of an entire industry, computational complexity, thinks of other models of computation that are more exotic. Non-deterministic computation, computation that's limited only in space, and so on and so forth. All those models are very interesting. Like the class, you've probably heard of the class NP. That's based on an alternative model of computation. We can't solve NP right now because the model of computation it's based on can't be realized, using any machines we know of that we can build. But there is a challenge to the strong Church-Turing thesis, probably as you well know. What's the challenge? Did you just make a Q? Yeah, exactly, quantum mechanics. So the challenge is that among all, the physical process we don't know how to simulate are the processes of quantum mechanics itself. And it was Richard Feynman back in the 80s who first really made this point explicitly, that if you want to simulate quantum mechanics, you should build an explicitly quantum mechanical computer. And then the kinds of exponential overhead that we encounter when we try to do it on a regular computer shouldn't be an issue. And that indeed actually does seem to be the case. And it hasn't really fully been done yet, but we may be on the road to proving something like the strong quantum Church-Turing thesis, where we could prove that any computation that could be physically realized physically could be simulated on a fully quantum mechanical computer. So our real challenge right now to the strong Church-Turing thesis is quantum computation. Now, I want to introduce you to some very simple quantum computations, but to do that, we actually have to be a little bit more formal about quantum mechanics. That one, we could use words all day long, and those words would be uncomfortable, or it would seem like it the words can make things mysterious that with a tiny, tiny little bit of mathematics become completely unmysterious. So we're going to do a tiny little bit of mathematics, but not a lot. All right, so our quantum info primer. Let's start here. So classical information, classical computation, as you well know, you can boil it all down to bits, right? And your bit is just some system that can take the values 0 or 1. Typically, you're able to set those values effectively. You can read them. You can manipulate them. You can interact them with each other. And the basic building block in quantum computation is just the qubit. Not because all of the physical systems in the world are built out of qubits, but because from an abstract perspective, it captures the essence of what's going on in the same way that bits capture the essence of what's going on for classical computation. And when we talk about qubits, just notation, I'll put a little flag on them, right, to indicate that's the state of a quantum system. So it's just a little notation. So a flag means it's the state. And we can talk about some examples, just to make it concrete. What might be a 0 and might be a 1. So I started you off. We had a photon. And if it was propagating horizontally, we called that a 0. We could call that a 0. And if it's propagating vertically, we could call it a 1. Anyone else want to suggest something that could act as a qubit? There's two distinguishable quantum mechanical states.
Clockwise current.
Excellent. Right. So I think there are people here who, well, there could be various reasons for that. But if you attended Steve Kivelson's or Sean Hartnell's lectures about superconductors, they spoke a fair amount about persistent currents. Oops. So you make a loop of some superconductor, and if the current's going counterclockwise, let's call that a 0, and clockwise, we can call it a 1. And that turns out to be, if not a great qubit, then not a bad qubit in many purposes. So many of you have probably heard of D-Wave, the company that claims to have built a quantum computer, although they haven't. Their qubits are qubits of this type. They're all superconducting current loops. And anyone want to suggest any others? Yeah?
Maybe an energy level in an ion?
Oh, good. OK. So let's, I'll just draw this. I'm writing small here. I apologize. So ion. So let's draw a little nucleus and put an electron there. Maybe if it's in its ground state, we'll call that a 0. And if it's in an excited state, a particular excited state, we'll call that a 1. Let's actually fix, put in a magnetic field so it's fixed, so there aren't additional degrees of freedom. Oh, you're giving an example. Oh, OK, good. Yeah. So polarization of light. So if it's polarized this way, well, versus that way, for example, two perpendicular directions. And we could go on all day, right? Because any two orthogonal states in the world, two distinguishable states could be qubits. Most of them are really bad qubits. This is a list of pretty good qubits from the points of view of actually trying to use them for things. Now, what is different about qubits as compared to regular bits? It's that these little flags actually mean something, which is that the states are vectors. So bits are just sort of primitive objects. They have no structure, right? But qubits have a little bit of extra structure. They're vectors, and we can just, each orthogonal state, or each distinguishable state of a system corresponds to a vector, and if they're distinguishable, they're perpendicular. Right? So we could draw our 0 and our 1 this way. And all the other states in that vector space are also valid states. Well, let's say they're unit vectors. So their length is fixed. And so superposition manifests itself just by having other states in the plane, right, that are of length 1. So those are also valid. And so this one here that I've called plus is an equally weighted superposition of 0 and 1. So equally weighted, if we want to preserve the length, means that, all right, a 0 plus 1, like so. And this one here, I'll call it minus. It has some positive 0 component and some negative 1 component, like so. So those states exist. They are real states, and they may be hard to make, they may be easy to make, but for a lot of these examples, they're relatively easy, like polarization, right? Nothing really specifies that vertical and horizontal polarization is in any way preferred over diagonal polarizations. So these superpositions are actually pretty easy to make. It may be harder in the case of the current loop, but it can be done. And this is how mutually exclusive states in quantum mechanics can coexist, right? It is in this sense that the actual physical state of the system is a vector, and we can have linear combinations, right? Which is a lot like probability, right? If you think about, if you want to model probability, if 0 was one possibility and 1 was another possibility, if we put probability weights in front of them, then we'd have a vector. But the difference is that with probabilities, only certain weights are allowed, and particularly, we're not allowed any negative weights. In quantum mechanics, we're allowed negative weights. And in fact, we're allowed more. Our weights can be complex. But it turns out that at least as far as information is concerned, that doesn't make a big difference. The big difference is in allowing negative numbers. And so I think that I'll be able to do without the complex numbers for the most part here. So the real difference is that we can have negative numbers, and those negative numbers lead to interference, right? That in the example that I erased before, the photon passing through half-silvered mirrors in an interferometer, the reason the different branches could interfere and cancel each other out was because there's a minus sign in there. All right. So the other thing, we're actually halfway through all you need to know about quantum mechanics to talk about quantum computation, which is remarkably little. But we need to talk something about, let's say, evolution, state transformations. And all we actually have to say is that the allowed evolutions are evolutions that take these unit-length vectors to unit-length vectors, right? That's the restriction, right? So we have to take states to states. So they have to preserve the length. So can anyone give me examples of transformations that preserve the lengths of vectors? Just in general terms? Rotations, right. So if I rotate, the length is preserved. And there's another class, reflections, right. So rotations and reflections. So if we ignore the fact that these weights can be complex, these amplitudes, so amplitude is just the coefficient appearing in here, then rotations and reflections is the whole story. So let's do a little example just because I like this example and we're going to use it later. So an example, let's see if we can construct a transformation that sends 0 to plus and 1 to minus. So this thing has a name. People call it, well, people call it various things, but we'll call it, for the moment, the Hadamard gate. So let's try to do it using a sequence of rotations and reflections. So we start off with 0 and 1. Anyone want to propose a rotation that might be a sensible rotation to apply in this setting? You're not going to get all the way there. So if you can't see how to do it with one step, what a rotation.
45 degrees.
Thank you. Yeah. We have a precocious 77-year-old in the audience. All right, so let's rotate by 45 degrees. And that way. So then we'll end up with these two vectors. And this one is already our plus vector. And this one is minus our minus vector, right? Because minus is down here. So how can we finish the job? Exactly. So now then we reflect. So we put a diagonal axis to reflect along. That leaves plus invariant, and it gives us our minus. So we've done it. So with rotations and reflections, we can implement this little transformation. And I do apologize. I'm just going to swap these out for a second. I don't think we really need it. But if you're uncomfortable with this picture, or this notation of the 0 flag and the 1 flag, if we have a qubit, we're talking about a two-dimensional space, like the plane, right? And so we can, the vector that corresponded to 0 was the two-dimensional vector 1, 0, and the vector that corresponded to 1 was 0 and 1. And we can write that this Hadamard gate, what it actually does as a matrix, we wrote it down over here in terms of these things called kets, these flags. But it's a little 2-by-2 matrix that looks like this. All right, almost there. So we have a way of talking about quantum mechanical states that are distinguishable. Those are orthogonal vectors, perpendicular vectors. We have a way of talking about superposition. That is linear combinations of vectors, vectors that aren't perfectly aligned with the axes. We know what the allowed physical transformations do. They just take states to states, which means they actually have to be compositions of rotations and reflections. And the last step is the measurement step, which we might as well finish with. And so measurement. What you do is you design some apparatus that basically asks the system effectively, which of two distinguishable states are you in? And that forces the system to effectively choose one or the other, probabilistically. So the probability is just the modulus squared of this amplitude. So amplitude is just the coefficient appearing in the vector. So in the case of plus, 1 over root 2 and 1 over root 2. And so the amplitude squared, if you were to actually perform a measurement in a plus state of 0 and 1, you'd get probably 1/2 0, probably 1/2 1. And the state collapses is the word often used to, let's say, the proper outcome. And there's more to say, but to understand the basics of quantum computation, amazingly, this is enough. And that might seem strange to you, that you can talk about quantum computation knowing so little quantum mechanics. But stop for a minute. Again, a number of you put up your hands when I asked if you work, or if you're a computer scientist. If you're a computer scientist, you don't need to know much about the guts of your computer, right? That's kind of the point of computer science, that you abstract away a lot of the physical details and then think in these higher level terms about the way information is processed. That's incredibly useful, right? The whole story of computer science and the incredible tools that we have available today is just layers upon layers of abstraction. And in quantum computation, in many respects, it's the same story. We talk about qubits precisely so that we don't have to discuss all of the more detailed complications that come from having an actual physical system. If someone wants to build a quantum computer or some other quantum device, they need to know a lot about the actual physics. But if you want to program it, so to speak, hopefully you don't. And today we're going to be talking about programming. So I should stop. Are there questions or objections? Objections are particularly good, but
Is it really correct that you don't need to know about complex numbers to think about quantum computation?
Yes. Yeah, no, so that's correct. So the question was, is it really true that you don't need to know about complex numbers to think about quantum computation? And the reason is that with 2 qubits and rotations, you can basically implement a complex structure, right? You can have with rotations, you can have the multiplication by I. And so there's a cost of, you have to double the number of qubits, and it's cumbersome. I mean, complex numbers, I'm skipping them now just because if people aren't familiar with them, I don't want to scare them off. But they're computationally phenomenally useful. That's a loaded word. Like we use them all the time in engineering and physics because they're really handy to calculate with. I hate remembering trig identities, but I can remember that e to the I, x plus y is e to the I x times e to the I y, which is all you need to know about the exponential. So the answer is yes, but you wouldn't want to. Yeah, usually. Yeah?
I have a history question. 25 years ago, I learned quantum mechanics. It's all very similar, but no one ever mentioned quantum information. Why
So
is that?
25 years ago puts us in the early 90s, and that's basically because that was before. Well, I don't know. I mean, you can still take quantum mechanics now, and no one bothers to mention quantum information because quantum mechanics, your quantum mechanics classes have various objectives, right? And one of the important objectives, perhaps the most important objective, is to teach you how to calculate the kind of quantities that are relevant when you're studying physical systems in which quantum mechanics plays a role. You learn how to find the energy levels of the hydrogen atom. You learn how to study simple systems, the harmonic oscillator, so on and so forth. And so all of those things are incredibly important, and they're still important. And a quantum mechanics class or a course in quantum mechanics, starting from scratch, that didn't tell you about any of those things would be doing you a disservice. But since 1990, and particularly what really changed is 1993, Shor's algorithm, which we'll get to later for factoring, that really drove home the point that if you built information processing devices in such a way that they could really take advantage of superposition in logical terms, that they could do things that would otherwise be impossible. And when you were taking your class, I guess that was not yet known, and so no one would have mentioned it. Yeah?
You said eBay probably hasn't built a quantum computer, so I guess my first question is what's lacking, and B, what's the main roadblock to actually creating a viable quantum computer?
Okay, so that is a that's a whole can of worms. So I'm not going to say too much about it. I'd say that from my perspective, building a real quantum computer, I haven't talked about exactly what the quantum mechanical equivalent of logic gates is, but you have to be able to perform logic gates, and you have to be able to perform a lot of them before the state of the computer is overrun by noise. And in their system, they can't apply logic gates at all, and even then, the noise rate is very high. So they have a different model of computation that's designed to solve optimization problems. And so it's sort of in principle, so it's a different model. If you could build that model really, really well, then you could actually do quantum computation in the sense that we mean. But their system is just not anywhere close to that standard. It doesn't mean that it's not interesting. So my little caveat about this is that there's some bad blood between D-Wave and other people who are thinking about quantum information. And so when some of their highly publicized results came out, computer scientists sat down and said, OK, we're going to show that we can simulate the D-Wave machine efficiently on a classical computer, which they then proceeded to do very effectively. So that the most effective way of running the D-Wave machine is not to run the D-Wave machine, but to run a simulation of the D-Wave machine on a laptop, which is faster than the D-Wave machine itself, and only costs about $1,000. But having said that, people who were engaged in this effort realized that their code for simulation ran pretty quickly, and actually was pretty good at solving optimization problems. So they tuned it up, and there's an annual competition for combinatorial optimization, where people are given random optimization problems. And so the competition happened this year, and the world's best optimization algorithm for classical computers on random combinatorial optimization problems is, roughly speaking, a simulation of the D-Wave machine. So, there's value there. Not what they expected, but all right. So we have measurement. We have all the pieces we need. And so now let's take a first step towards challenging the strong Church-Turing thesis. It's going to be a really little baby step, but one that nonetheless, surprisingly, captures the essence of a lot of what's going on in quantum computation. All right. So I'm going to exercise my limited artistic abilities. I'm going to draw a switch. So here's a switch. It can go up or down. There's a switch. And here's the light. Yeah, OK, I hear you. So the incandescent bulbs may be, those look probably incandescent up there. All right, so we have a switch and we have a light. And my task for you is to give me a procedure to determine whether the switch is connected to the light. Could anyone solve that challenging engineering quality assurance problem? Yes?
Measure the light, flip the switch, measure the light again.
Beautiful. OK, so our question is the switch connected to the light? And to find out, we must, I'll say, use the switch twice. Right? We have the switch in the up in the up position, we look at the light. We turn the switch to the down position, we look at the light. This is pretty obvious. It's pretty obvious also that you can't do any better than that. That if you never flip the switch, you will never determine whether the switch is connected to the light. And in fact, if you were here at the beginning, we were quite challenged by determining which of the many switches in the box down here was connected to the lights. And we were somewhat unsuccessful. Or maybe we just determined the answer is no for some of them. All right, so. OK. So you may not understand because this. Yeah. That's it. I mean, this is not a challenging problem. Well, OK, so you don't have to flip the switch twice, but you have to observe the state of the light for 2 positions of the switch. Yeah. So I guess using the switch, 2 observations. Yeah. I guess using the switch is a bit misleading. Yeah.
You're assuming the switch works and the light.
Oh yeah, right. We're assuming the light works. And the switch works. Yeah. Although if the switch doesn't work, then I think the answer would just be no, roughly speaking. No? It can fail in other ways. There are other failure modes. OK. Let's say we assume that both the switch and the light are in good working order. All right. So my claim is that in a sense which is really not cheating, with quantum mechanics, you only need to use the switch once, or you only need to make one observation. And this was this is actually known as Deutsch's problem. I should mention his name. Someone was asking about why they hadn't heard about, they didn't learn about quantum information when they took quantum mechanics around 1990. I think this is from around 1985. But as you'll see, the problem is not terribly challenging, and so it was probably not worth mentioning in your quantum mechanics class. But it's nonetheless suggestive. So we just need to actually do this, and we're going to do it for real. We need to be a little bit more formal. So I need to use a little bit of math again, but just math on the level of what we did here. And in fact, using little bits and pieces that we had there. So we're going to have that we're given some function. And so the function has an input, which can be a bit, 0 or 1. And that's the position of the switch. So this is our switch. And then it gives us an answer, which is also 0 or 1. And this is the state of the light. So maybe 0 means the switch is down, 1 means the switch is up, 0 means the light is off, and 1 means the light is on, right? And so we can capture the question that we asked above in terms of f, right? And our question was which holds? Is f of 0 equal to f of 1, right? So if the value of the light is independent of the position of the switch, that means that the switch is not connected. So that's not connected. Whereas if f of 0 is not equal to f of 1, then the switch is connected to the light. Because the light state depends on the position of the switch. So we're going to solve this problem using quantum mechanics. And I guess we can delete all of this. Oh. And to do it, I have to tell you what it means to have a quantum mechanical switch, right? And there are different ways of setting this up, all of the reasonable ways are equivalent, okay? So I'll give you the simplest one. So, so we have a quantum switch and light. And it's a box, right? So you give it a qubit, and you run it through the little machine, and what comes out, depending on the value of x, depending on the value of the switch, which can be 0 or 1, you change the coefficient in front of x, right? So remember that in quantum mechanics, our states have these amplitudes, and so this is, I don't have time to really get into the details of how you'd build such a thing, but this, I'll assert to you that this is not a cheat, right? That to the extent that it means anything to have access to a quantum mechanical switch and light, this is a reasonable definition. And so this is a transformation that we can apply to our system, but somehow the transformation, we don't know what it is, right? Because it depends on f. Right? So it's some box that somebody builds for us, and we want to learn a property of f, but we only want to use the box once. That's going to be our goal, right? So in the classical setting, we had to use the box that runs the switch twice. We're going to work out the answer to our problem with only one use of the switch. Yeah?
The phase factors don't affect the state.
Excellent point. Okay, so the observation was that phase factors in general in quantum mechanics don't affect the state. And that's true of global phase factors that you can factor out of the whole state. But the way that this box works, if a superposition of x's comes in, a superposition of x's comes out with the phases messed up. And they're now the relative phases that get changed. Does that make sense? So, right, it looks like this is a global phase, but if there's a superposition coming in, because quantum mechanics only allows rotations and reflections, which are linear, this also tells us what happens for superpositions. I guess I did gloss over a little bit of the laws of quantum mechanics there. Other questions or objections? All right. If not, what features of quantum mechanics do you think might be relevant to making this thing work? Yeah. Superposition. That is very true. So let's start off by making a superposition. So we'll start off with 0. And we saw above that we can use this h. So time is always going to run to the right. So we can use this h to make a superposition, right? I'll use a different color. So we'll have 1 over root 2. I'll just drop the actual normalization doesn't matter. So I'll just say the state here is going to be 0 plus 1, which is plus. So if you have a 0 that comes into this Hadamard gate, what comes out is a superposition of 0 and 1. So we've created a superposition. And what we're now going to do is we're going to run f. Right? We're going to actually apply the switch in superposition. And this is something that you can't do with classical computation, right? So here we're making use of the power of quantum mechanics. That classically we had to use the box twice because we need to check the value of the function for 2 different positions of the switch. Quantum mechanically, we can use the same box once to check the switch sort of in 2 positions. So what comes out here is, let's say, -1. I should write it big. -1 to the f of 0, 0, plus -1 to the f of 1, 1. So that's kind of mysterious. There's some math on the board, which I apologize for. So we don't know the value of f of 0 or the value of f of 1. But we don't care about their values. We only care about whether they're the same or different. So if they're the same, then the phase in front of 0 is the same as the phase in front of 1, right? So if they're the same, then this is plus or minus 0 plus 1. We don't know whether it's a plus or a minus, but we know that the phase is the same. So this is if f of 0 equals f of 1. And conversely, if they're different, then the sign in front of 0 is different than the sign in front of 1. We don't know what the value is, but we can write it this way. So what we've succeeded in doing is producing 2 perpendicular states depending on the answer to our question, right? They're not the 0 and 1 states. They're rotated by 45 degrees, or rotated and reflected, according to the Hadamard rule that we saw before. But they're pretty much what we want. So this one is plus or minus times plus, and this one is plus or minus times minus. And so could anyone suggest a way to fix this up a little bit so that our answer is either 0 or 1? Yes? So if we apply another Hadamard, what comes out is plus or minus 0 if f of 0 equals f of 1, and plus or minus 1 if f of 0 is not equal to f of 1. So Deutsch made this, so this is the solution to the problem. Because at this point, the state is 0 just measuring the system will give us the answer to the question. So here I'll just draw another one of our little detectors. At that point, we measure the state, and it gives us the answer. And so we have solved the problem using only one use of f. So that's it. This is not a tremendous savings, right? Despite the fact that we were confused a little bit at the beginning of the lecture about how these lights were connected, we don't usually think of determining whether a single switch is connected to a single light as a hugely challenging problem, and getting from one use of f to, or two uses of f to one doesn't seem like a huge improvement. But this does contain, surprisingly, the essence of quantum computation. That what's going on here is a use of interference to actually, superposition to evaluate some function on many inputs at once, and then interference between the different values of the function in order to do something useful. A combination of the two. You'll often hear people say that the power of quantum computation is that you can, with superposition, you can run a computation in parallel on all the different values of the input at once. And that is true, but only in an extremely limited way, right? That if we were to measure at this point, we just get one outcome of f, right? At random, which is not terribly useful. So the real challenge in quantum computation is using the combination of the fact that you have some inherent parallelism that you then have to combine with some interesting interference to get anything useful out of it. All right, so let's try to come up with this is not usually a good thing to do, but let's come up with a grandiose interpretation of what we just did. Usually the correct strategy in any given situation is to come up with the simplest possible explanation and interpretation of what you've done, but I want to come up with a grandiose interpretation. The reason being that it turns out that, in the grandiose interpretation, this is a special case of something much more powerful. And the more grandiose interpretation is that we're finding the period of a function. So what is the period? All right, if you have some function like a sine wave, so this is 2 pi, 360 degrees, 4 pi. The sine function repeats itself, right, as it goes along, and there's a relation that the sine of x is equal to sine of x if we shift by 2 pi. That's what periodicity is, and the period is the number that we shift by in order to get the same value. Okay? So let's write down some slightly strange arithmetic. And in my arithmetic, I'll say that 0 plus 0 is 0. 0 plus 1 is 1. And 1 plus 1, well, we all know that's 2, but I'll set it to 0. Okay, so in my binary arithmetic, I have no way of expressing 2, so I'll say 2 is 0. So you can read this as even plus even is even plus odd is odd plus odd is even. Okay, so this is binary arithmetic. And our condition that f of 0 is equal to f of 1, we could write this as f of x is equal to f of x plus 1, right? That if x is 0, then f of 0 is equal to f of 0 plus 1, which is f of 1, right? And likewise, as f of 1, it's equal to f of 0. And if they're not the same, then the best we can do is say that f of x is equal to f of x plus 0. Right? In terms of periodicity, the only periodicity is totally trivial, right? That if you don't shift at all, then the function doesn't change. And so our grandiose interpretation of this Deutsch problem that he came up with back in the 1980s is that what he's really doing is he's finding the periodicity of this function. It was hard to see that at the time because a function with only 2 values, it's hard to see that it, that's what it was all about. But that is what it was all about. He was finding the period of a function. And it turns out that quantum mechanics and quantum computers are really, really, really good at finding the periods of functions. And that is why Shor's algorithm works. Okay, let's go up here. Again, questions or objections? Yeah.
We have analog systems that can do the Fourier transform. If I have a hair of a specific length, it's going to vibrate based on the periodicity with sort of one sampling.
Yes,
If it's Seaman Copley, it's not a quantum computer.
Good. So let's hold that thought, and we'll discuss it in just a moment. Yeah, so there are systems out there that naturally implement Fourier transforms, diffraction and others. Why can't we use those to factor large integers? And we'll have to think about it. All right, so the first point, I wanted to erase this. So let's talk about factoring. So a first point about factoring. Why should you care about factoring, right? And I would kind of argue that you shouldn't care that much about factoring. So the NSA cares about factoring because the security of modern public key cryptography systems is based on the fact that we can't factor large integers efficiently. And that's the main reason people care about writing algorithms for factoring. But if you manage to find a good way to factor, no one would use those public crypto systems anymore, right? There's built-in obsolescence to a good algorithm for factoring. I think when I taught this, I was trying to come up with an analogy, and I was thinking back to the 19th century. And at some point, they had steamer ships and these whalers. I don't know why this one came to mind. So whalers, they built these great big whaling ships that could steam through the ocean with harpoons, and they were fast, and they killed tons of whales, and then there were no whales to kill. And then the technology of big, fast whaling ships was completely useless. So factoring is a little bit in the same category. So we don't build a quantum computer unless we're the NSA to factor. We build a quantum computer to simulate physics, to simulate chemistry, right? In Steve Kivelson's talk, also Sean Hartnell's talks, there are mysteries about the origins, for example, high-temperature superconductivity, interacting many-body quantum systems. We don't have good tools for understanding a lot of them. We could simulate them efficiently on a quantum computer. I think that's the killer app, right? That's the one that's not going away. Factoring will go away. However, it turns out that the same underlying tools that are useful for a factoring algorithm, strangely, are also useful for simulating physics. So let's talk about factoring just a little bit and get a sense for why it works. So the first point, and all I'm going to say about it, is that this is true. It's good enough to find periods. All right, so this is just classical number theory. I think this has been known since the 19th century. So there's nothing new there. If you can find periods, then you can factor. And the kind of situation that we're interested in with factoring is factoring a large integer. So what does large mean? It means it has a lot of digits, right? So we're going to factor some number m that, say, has 4,096 digits, which is, I think, what's currently recommended for RSA. Now, it turns out that the function that's associated with this situation that you want to for factoring, whose period you want to find, so the period p, this is the period. How big do you think it might be? Knowing nothing else. big. Your period, generically, is also going to be a 4,096-digit number. Maybe 4,095. I don't know, maybe if you're lucky, right? But your period is going to be a huge, huge number, right? And so if you have a physical system, to come back to the question that was asked earlier, which is capable of implementing the Fourier transform, is it capable of implementing the Fourier transform on a state space of 10 to the 4,096 items, with keeping precision? And the answer is going to be no, right? You're not going to be able to distinguish the states with exponential precision in a cochlea or in a diffraction experiment or anywhere else. So you need the discreteness of a quantum computer, and you need some other way of implementing the Fourier transform. Well, I'm using the words Fourier transform because it came up in the audience, but I haven't told you what Fourier transform is. So if you have a function, well, I drew one over here. Well, so we have some function. Again, let's say it's simple, and it has some period p, and there's some big number n here, and you want to find the period. This is a very well-established, there's a very well-established mathematical tool for doing this, and that is what's called the Fourier transform. And this is just how you extract the harmonics in a given function. And so we can hear them, as was pointed out, to some degree. But mathematically, it's known how to do this. And what comes out is something like a spike at n over p. Boop. So there's some well-defined procedure that given a function, if you want to find the period, you run it through this Fourier transform, and it gives you the answer. Now, the obstacle to applying it in the situation that I described is that if you try to run the Fourier transform, as it's usually implemented, on a number that's this big, it's going to take far, far, far too long. And that's really the obstacle. But surprisingly, it's still useful to think about how we do it. And so let's just talk a little bit about how we calculate the Fourier transform. I haven't even told you exactly what it is, but you know intuitively what it is. It's the transform that pulls out the harmonics from a given function. So here I've written something really simple, but the actual function whose period we want to find has very little internal structure other than the fact that it's periodic. It doesn't look nice and simple, which would make it easy to find the period. It's just a scattering, a total mess of points that happens to be periodic. So there's a naive way, if you have the definition of the Fourier transform, to calculate it. But there's an algorithm. It's called the fast Fourier transform. And nominally, this was invented back in 1965 by Cooley and Tukey. I'm sure many of you have used the fast Fourier transform. And it's a way to compute the Fourier transform that's a little bit faster than the naive method of calculating it. One of the funny things about it is that Cooley and Tukey were not the first people to do this. It turns out that Gauss, back in the 19th century, was trying to infer the periods of the orbital rotation for some objects in the sky. And so he wanted to expand things in terms of their harmonics, find out their periods. And he got tired of writing down the naive expression. And so he invented what is the modern-day fast Fourier transform. And in his notebook, he writes, the efficacy of this method will become apparent to anybody who tries it. And he only had something like 15 data points, right? He didn't have a 4,096-digit number to worry about. So how does it work? So let's put a number n on there. And so n is some... So we're going to have to represent the number that we're factoring on a computer. So we're going to use bits, say. So let's say that the biggest number we can represent is capital N, which is 2 to the little n, where little n is the number of bits. So we want to calculate the Fourier transform of this capital N, which is a power of 2. And Gauss's observation, repeated by Cooley and Tukey, is that there's a nice, interesting internal structure in the Fourier transform, which is that if you want to calculate it, you can break it up into 2 subproblems, each of which is half as big. Right? So you have a sequence of length n, like I've drawn right here. And what you actually do is you take all the even points, and then you squash the function down, and you calculate the Fourier transform of the even points. And then you take all the odd points, and you calculate the Fourier transform of the odd points. And then you mesh them back together again. And that's the observation. And so the algorithm is just to say, well, if I can break it up once, I can break it up again. So I'll take the evens, and I'll break it into the things that are divisible by 4 and things that are not divisible by 4, and so on and so forth. And all the way down until you're calculating the Fourier transform of a single element. And I haven't told you what the Fourier transform of a single element is, but can anyone guess? The Fourier transform of a single point? It's the same. It does nothing. So we know how to do the thing at the bottom of the tree. So here's the algorithm for the Fourier transform. You just break it up into these pieces. And the height of this tree is the number of times you had to divide by 2, right? But our number was 2 to the little n. So this is height n. And it turns out that when you take these two Fourier, the even and the odd Fourier transforms and put them together, there's a cost at each level. And the cost of putting together 2 Fourier transforms of size n over 2 is n. The cost of putting together 4 Fourier transforms of size n over 4 is n over 2 plus n over 2, which is n. So you have this additional cost of n at every level. And so the total cost is little n times 2 to the little n steps, right? Because 2 to the little n is big N. All right, so we have a big N is a 2 to the n. Well, so at each, we have the cost at each level is capital N, and we have little n levels. So the total cost is little n times big N. So this is the cost means the number of computational steps. Reasonably defined. And the basic point is that even though this is the fast Fourier transform, the running time is exponential in the number of bits, right? So this is not useful to us if we want to find the period. And if it had been useful, then someone would have noticed a long time ago that with the Fourier transform, you could factor large integers. However, if you take this same algorithm and say, well, we want to do this on a quantum computer now. We want to prepare a superposition over different values of our function whose period we want to find, and then we want to apply a Fourier transform to that function. Then it turns out that these different branches in the fast Fourier transform, you can evaluate them in superposition. You don't need to do this one and that one separately. You just do it once. You don't need to do this one and this one and this one and this one separately. You just do it once. And the process of assembly is also much more efficient, which the details I won't get into. Oops. So on a quantum computer, evaluate the branches in superposition. And the cost, the computational cost, the number of little elementary quantum logic gate, ends up being the height of the tree times an assembly cost, which is now much better. It's just a little n instead of a big N. So it's n squared. And so on a quantum computer, we can implement this Fourier transform exponentially faster than we can on a classical computer. And what it does, just to be clear, if we had some superposition, some function f of x, so we have some function over values of x, f of x, like we have right there. Then our Fourier transform maps this to f tilde of x, where f tilde is the Fourier transform. So if we had a sine function that was periodic in our amplitudes, what we get out is a spike, right, in f tilde. So that's what this transformation does for us. And I don't know if it's really worth going into much more detail, but this is why Shor's algorithm works. That we prepare, there's a periodic function associated with factoring. We prepare a superposition of inputs. We evaluate the function. We run a Fourier transform, and then we measure the result. There are complications in the story, but the key reason it works is really that the Fourier transform can be implemented really efficiently. Now, those of you who are familiar with the Fourier transform may be asking at this point, wait a second, the Fourier transform has lots of applications that are more important than factoring, right? Who here in the room has used a Fourier transform? Yeah, okay, good. So there are lots and lots of applications of the Fourier transform in signal processing and quantum mechanics, obviously, and elsewhere. Now, the reason it's not universally useful is we get a superposition, or we get a Fourier transform of the amplitudes, right? But in signal processing applications, what you have, there's some, say, vector of numbers that you measured, say, over time. So it's a list of numbers you have in your lab, and you want to calculate the Fourier transform of that list of numbers. That list of numbers is not the amplitudes of some state in quantum mechanics, right? And you actually want to know what the numbers are at the end. You don't just want to have the Fourier transform embedded in the amplitudes, because then what do you use it for, right? And so the reason that, on the face of it, being able to implement a Fourier transform exponentially fast looks like it should be amazing, right? But the applications are more limited than that because it's a Fourier transform of the amplitudes. And finding a way to use it requires some cleverness, right? Like what I've sort of sketched out here. Perhaps it's worth saying, since everybody hears about factoring, this is like the old chestnut now in quantum computation. There's an impression that that's all a quantum computer could do. So it's worth pointing out, this is also this is also an application with built-in obsolescence. But other public key crypto systems that are out there, like elliptic key cryptography, they're not based on the security of factoring, but they're based on other the hardness of evaluating other number theoretic functions, like the discrete log. Those can be cracked as well. Like those can be run efficiently on a quantum computer. There are lots of speedups that are not exponential improvements over what's best known classically, but that are polynomial speedups. In fact, those are, I would say, go as far as to say those are generic, right? You give me a computational problem. If I spend some time at it, I can probably get you a speed up. Maybe it goes from running time n squared to running time n to the 4/3 or something. That's only useful if your quantum computer is really fast. And at least in the near term, people talk about building quantum computers. The overhead in running them is going to be so high that it's really these exponential improvements that we care about a lot. But there are some other ones out there that are also seem pretty interesting and important. One of them being that you can do linear algebra really quickly on a quantum computer. So something that many of you, if you've used Fourier transforms, you've also tried to solve equations of the type AX equals B. So inverting a matrix A. On a quantum computer, suitably defined, you can do this much faster, exponentially faster than it takes to write A down in the first place. Which indicates that there's a caveat, of course. So the problem is, of course, is the same kind of situation, that if your vector x is the vector of amplitudes for a quantum state, then you can invert, you can act with A inverse on x as a quantum state. So you get the answer to your linear algebra problem as amplitudes of a quantum state and not as an actual answer you can put your hands around. But there's been work recently on, say, using this type of quantum algorithm for machine learning purposes. And that actually looks like a promising domain, like an area where lots of linear algebra is being used. They're very large data. But it's early days.
You say you get the answer as the amplitude of a quantum state.
Yeah.
You just mean you get the amplitudes of a quantum state. What do you do with that?
That's the problem, right? Yeah, so then you measure an observable, right? So you have a quantum state whose...
You talked about before of the interference, which...
you use the interference in the creation of the algorithm. But in some circumstances, Yeah, so say that you have this vector b. Yeah, yeah. In some circumstances, like some gradient descent algorithms, you don't use the whole solution. What you do is you say take the dot product of the solution with some other vector. And so that dot product is the kind of thing that you can access as an expectation value of some observable. So there's a subsequent step where you perform a measurement on, or I guess it's x here.
Many measurements.
Right, so if you wanted to learn it very well, you might have to perform many measurements. It depends on the situation. Like, so this is a bit off topic, but you've probably heard of deep learning. Well, of course your son does deep learning. So there's a gradient descent step, but evaluating the gradient would actually be very prohibitive time-wise because it's a very high dimensional space. So what they do is they just do a stochastic sampling of the gradient. They just choose a random direction, or a few random directions, take directional derivatives, and then use that to estimate the derivative. And so, so random sampling of this kind of thing can be useful. I mean, one has to pin it down, but it's a non-empty set of situations in which it's useful.
Well, there's a famous statement about quantum mechanics. You can't measure the state of a quantum system.
You can't measure the state. You can calculate expectation values of observables for those states.
You have to do the experiment repeatedly many times.
So yes, but if you only care about the average value, right? It depends on how you're going to use this number. Like I agree, it's a subtle question, but I wanted to give the deep learning example because there you don't actually get the they don't use the exact gradient. They use some sampling of some distribution whose average value is the gradient, and that turns out to be good enough. And so this is sort of in the same spirit, the kind of thing you could do. Yeah, so there are potentially lots of applications. The short-term ones, meaning 15 years from now when we manage to build one of these things, are going to be things like factoring, simulating a quantum computer, but hopefully more than that. And in the Monday lecture, we're going to move away from quantum computation. Well, somewhat. We're going to talk about quantum entanglement, the phenomenon of quantum error correction, and as I said, or as I suggested earlier, how that's related to decoding the hologram of the holographic principle of quantum gravity. So thank you for your questions and your attention, and I'll see you next week. I guess I cut you short a little bit, yeah. So are there additional questions? Yeah.
Why stimulated emission
Good question. Okay, so there was a question, why does stimulated emission not violate no cloning? And it turns out, and this is quite a beautiful fact, that the process of stimulated emission gives you an approximate clone, which is provably the best possible approximate clone that's consistent with quantum mechanics. So it doesn't because of entanglement, it doesn't actually produce, like the actual process is not 1 photon to 1 photon, it's actually 1 to 3. And so you have to, there's additional entanglement with that third one. And if you ignore the third one, what you find is that you have a sort of noisy version of the original quantum state. And it's an optimal approximate clone. Let's see. So it's on. Unfortunately, it's not carrying through. I apologize for that. I'll speak more loudly. Other questions? Yeah.
So just to kind of go back to the Deutsch's problem. So you gave me this kind of like classical analogy where like you apply f successively on the states 0 and 1, right?
Yeah.
Then you gave the kind of like quantum analogy, but I was like, so strictly speaking, you didn't really apply it on like the states 0 and 1, right? Like you applied it on the states h0. And
Yeah, that's true.
So does that like, but nevertheless, like, I mean, applying the F gate does result in like an F of 0 and an F of 1. Nevertheless, I mean, I was just wondering, like, if you successfully just applied the F gate to 0 and 1, like, you wouldn't really be able to capture that phase difference that you would after applying the Hadamard gate and then applying it afterwards. So so it wasn't completely obvious to me that there's like some statement that says like you can't do some kind of like similar transformation on the classical side, like on the states 0 and 1, such that you only apply, the F, or I guess the equivalent version of an F gate, like only once.
Yeah, so what you have to, I mean, the first thing I'd say is a little bit of an admission that you can write down a formal notion of query complexity in which there's a strict difference between the classical and the quantum. But the demonstration that this is a useful idea is ultimately in the fact that you can do things like you can lift the observation that this Deutsch procedure works to a real algorithm that solves a real problem, like Shor, right? Like that I'd say, like, query complexity is kind of like, from the computer science perspective, computer scientists like it because you can prove things about query complexity, the number of uses of some function. And you can't prove anything in actual complexity theory. We don't know that P is different than NP and so on and so forth. And so it's this little playground in which you can prove things, but the meaning of the conclusions that you draw is kind of provisional because the model is a little bit separated from what you do in practice. And so that's a first caveat, that I acknowledge the objection. But the response is, so there are intermediate problems between Shor and Deutsch, right? Where we can actually see, like, we can look at families of problems that get larger and larger, and then separations between the number of queries, uses of the function quantum mechanically and classically. And the way that you make it meaningful is you imagine that you had some way, classically, there's some function, f, and you have to implement it on your computer. Right? So there's some number of steps that it takes to implement on your computer. So then you say, all right, now I want to implement that function f on a quantum computer. And the number of steps, and then you can show that the number of steps required on the quantum computer is basically the same as the number of steps on the classical computer. There's like a little bit of extra overhead, but it's not significant. And so if you had an efficient way to implement f on the classical, you get an efficient way to implement f on the quantum. And then if you had an improvement in query complexity, that means the total number of, total amount of time required to run the whole thing is now much, much better. But it requires looking at the internal guts of how you'd implement f to make it, to be sure that you're comparing apples and apples. You're right. Yeah.
So, what bothers me about Deutsch's problem is, okay, I get the transition to a superposition of states on the switch, but now my light bulb is both off and on.
Yeah, no, this is true. And this is why actually it should not be a light bulb. Because we haven't talked about noise in quantum mechanics, but we did see that you can't copy quantum states. If you measure them, you disturb them. And light bulbs are broadcasting to the world their state. And so it's really hard to maintain that superposition because it's going, that broadcasting of state makes it easier to measure the state of the light bulb elsewhere. We should use a cat. We should use it could be a cat. Yeah, exactly. So you're right. There's perhaps a better way to do the analogy. Yeah.
So what is the assumption about time behind superposition? Is there a background, Minkowski or otherwise?
It doesn't really matter too much. I mean, well, it does matter. So the way that I'm working here, I'm really assuming that we're in some inertial frame, and all of the components of this quantum computer are in this shared inertial frame. And if that were not true, there'd be additional complications to worry about. Like quantum mechanics still holds in that setting, but you might have additional noise, and so let's say that's the setup. I mean, the basic principles of quantum mechanics that I wrote down earlier, those are true independent of, well, at least the most radical assumptions about time. It's just the structure of quantum mechanics. There's superposition, there's measurement, and so on and so forth. Unitary time evolution, whatever time means. You might have freedom in your choice of what time means. It'd still be unitary. Yeah?
practical examples of what a qubit is, like, direction of a current in a.
Yeah.
What could be an example for a Hadamard gate?
Oh, good. So the very first example that I gave, which was a half-silvered mirror for a photon coming into into that mirror, that is actually pretty much a Hadamard gate. I mean, depending on your conventions, the phases might be a little bit different, but it's essentially a Hadamard gate.
If it was just a spin of an electron or something, it would just be the rotation of the magnetic field from the z direction
Yeah,
to
exactly.
the x direction.
Yeah, so that also does it.
Yeah.
There's a global phase to worry about, but we don't actually care about it. So, yeah.
There are a lot of proposed implementations from like ion trapping to measuring center to like major and fermions. Like, which approach do you think is most viable in the long run for building an actual quantum computer?
Right. So the question was, what approach do I think is most viable in the long term? And I'm not an experimentalist, and so I'm actually not an expert on this really. But at the moment, I'm most optimistic about superconducting circuits, particularly these transmon circuits that are being built in Delft and Yale and Google UCSB and elsewhere. So they have qubits. 10 years ago, maybe 15 years ago, no one thought superconducting qubits would be good qubits, right? Because they were overwhelmed by noise, just much too quickly relative to the amount of time it took you to do anything interesting. But the people who've been working on these systems, I mean, it's amazing, right? They have increased the effective lifetime by a factor of 10 every year and a half or so. And there's been a kind of Moore's law for longevity of the qubit state. And they're at the point now where, so we're going to talk about this on next Monday a little bit, but there are threshold theorems. If you can get the noise below a certain threshold, then you can scale up quantum computation arbitrarily large using software. And their gates are right around or below that threshold. Now, they don't have a lot of qubits, right? But they went from being totally useless to being good enough individual qubits. And then just by virtue of the fact that this is being done in solid state, right? One can be optimistic about scaling it up to to more qubits on the same chip. Now it turns out, and this is a little bit counterintuitive, given our experience with transistors, but the components of these superconducting qubits are actually pretty big. That there are resonating cavities for microwaves in there that are sort of micron scale, or maybe even bigger. So something you can actually see the features with the naked eye when you look at these chips. And so there is a limit to how many you can put in a reasonable amount of space. And so John Martini, like the people who are working on this, they feel that they have a clear roadmap for getting order 100 qubits on a chip, in the next 5-10 years or so. That they have perfect control on, they can do algorithms and so on and so forth.
Does that mean 100 physical qubits? Or
100 physical qubits.
which is maybe one logical qubit?
It depends what you mean. So it depends on your noise rates, right? So you might be able to do analog simulations, but it would still be impressive. But my point being just that from there is a big challenge for them still, which is what happens when you run out of space on your chip. So there's an interesting sort of sociological observation about this, which is I'm a theorist, and I've been doing this for a long time. I've been doing this since the late 90s. And back then, when these fault tolerance results first came out, all the theorists were saying, we're optimistic. They said, this is going to happen someday. We don't know if it's going to be 20 years or 100 years or 500 years, but because of these theorems, this is a technology that will eventually happen. And experimentalists said, you're crazy. That is never going to happen, ever. You have no understanding of what's really, what the real challenge is. And now the theorists that I know have a roughly the same level of optimism that they had then, because their optimism is roughly based on an understanding of these theorems about the underlying difficulty. But the experimentalists are much more optimistic, right? They say, oh no, we're going to be doing these exciting things in 5 years, 10 years that we actually thought might be 50 years away. And so there's been this shift great skepticism from the experimentalists to great optimism, and the theorists are sort of more damped in their, their estimates of when it's going to become reality. Yeah.
So there was some question of like, could you build a generic Turing machine?
Yes.
In the early days there, and then it turns out it's actually hard to not have your language be Turing complete. We keep accidentally making Turing complete type systems in our languages. What makes you think that we haven't accidentally made a whole bunch of quantum computers and that our iPhones are doing this and we just don't know how to program them?
Right, so there are this is actually a really interesting question. The first point is that there are universality results. That you can prove that if you choose the right set of sort of basic logic gates, that when you compose those, you can get arbitrarily close to whatever big unitary transformation you're trying to make on your quantum computer. And that if you have a universal set of gates, the number of steps is largely independent of the choice of universal set of gates. Right? So there's a universality theorem about quantum computation. Maybe I'll end there. But the interaction of that universality with fault tolerance turns out to be very interesting. Because what you can do fault tolerantly in a quantum computer is often much more limited than what you can do without protection from noise. And it's actually really important at the end of to get all of this stuff to work that you be able to perform universal computation with a discrete set of gates that are quite different, quite different from each other, that don't involve arbitrarily small rotations and stuff like that. So we're confident that we haven't fallen into that trap. But maybe one last comment on this, though, is that one can think of models of computation that are weaker than full quantum computation. And some of those are actually quite interesting. And people study them because they ask questions like, well, if we wanted to build a device that on good complexity theoretic assumptions could never be simulated by classical computation, what would it need to look like? And there are ideas for that are much simpler than building actual quantum computers. So those are less expressive, but they can nonetheless be shown to be expressive enough to not be captured by classical computation.
Say two hands up. In a word, what is a quantum gate? It's not much different than a logical gate.
Yeah, so exactly. So a quantum gate, I apologize for using the word without defining it. So you have some freedom in what you mean by quantum gate, but the idea is it should be some relatively simple operation that your hardware can implement in some unit, essentially unit time. And the standard logic gates in classical computer science are the NOT gate, the AND gate, the OR gate, and so on. But except for the NOT gate, which just flips the bit, the AND is not reversible. Right? You forget part of the input if you take an AND, and the OR is not reversible. But quantum mechanics is always reversible, right? Because you have to preserve the lengths of vectors. Rotations and reflections are always reversible. And so a quantum gate is a reversible small operation. So in practice, what we usually say is that we have a quantum computer of many qubits, and our easy gates are things that act on only 1 or 2 qubits at a time. And then to build up bigger transformations, you have to compose them with each other, a lot like logic gates.
So you mentioned, I imagine Leah Kornova at Delft or 1D nanowire. Are you going to be able to touch on topological quantum computing in any way in the next lecture?
I wasn't planning on it, but it's a beautiful and exciting subject. I haven't written 100% of my next lecture yet, so maybe yes, but I think that saying anything other than the vaguest, hand-wavy stuff requires a bit of time. And so I'll see if I can work it in, but no guarantees. If there's demand, I'm available. Yeah.
Thank you, Patrick.
Yeah.
For more, please visit us at stanford.edu.